3 a.m. local time, flames lit the Russian sky, and the story wasn't about one refinery, it was about reach. Ukraine's long-range drones slipped past layers that were built to stop missiles, not small machines, and oil hubs near Moscow, Ryazan, and Novokuybyshevsk paid the price in smoke and silence. For viewers in the US, this matters because cost now beats mass. A cheap airframe can bend an expensive shield, and when fuel stops moving, strategy slows down. The target list looked routine: pipes, tanks, hangars, but the message was not. It said that deep strikes are no longer rare, that timing can outplay radar, and that psychology moves markets before damage reports do. Tonight, we focus on what changed, how layered waves confuse sensors, why low altitude beats clean theory, what tricks turn a drone into a fake cruise missile on a screen, and how one quiet route can reach far places most thought safe. Stay to the end for the strategic read, because when defenses shift home, front lines shift too. Like and subscribe to Military Force for verified maps, clear sources, and sharp breakdowns that cut through noise. Pre-dawn timing gave Ukraine the edge because crews were thin and sensors were cold after a quiet night. This window let multiple teams move at once, and it kept roads clear so first responders reached gates late. Fires started fast at several sites around Moscow, Ryazan, and Novokuybyshevsk, and smoke columns were visible for hours. Operations paused for days at some plants since hot metal and toxic air stopped maintenance and delayed restart checks. From that timeline, the path of approach becomes the next piece to watch. The drones likely flew low because low altitude hides behind buildings and bends under the radar horizon. Rooftop height gives cover in cities, while river valleys and tree lines give cover in open ground. A steady speed helps batteries last, and a flat profile cuts noise, so most routes favor simple, quiet flight. Crosswinds matter over flat terrain, and cold air at dawn keeps exhaust close to the ground. Those conditions explain why pre-sunrise runs keep showing up in reports. Targets were not random, because refineries have choke points that break production when a single unit goes offline. Storage tanks feed pumps, and pumps feed heaters, so one crater can force a whole train of shutdowns. Coking units run hot and dirty, and a strike there risks long cleanups before safe pressure returns. Electrical yards are small but vital, because switchgear and cables are hard to replace on short notice. These features turn a modest blast into days of lost output. Video from nearby towns showed bright flames and heavy smoke, which suggests liquid fuel and plastics were burning. Heat like that warps beams and lifts roofs, so a hull can fail even without a second hit. Foam lines need stable pressure, and hoses kink under debris, so fire crews fight the clock as well as heat. When a plant sits dark, rail schedules slip and regional stocks tighten, so the shock spreads beyond the fence. That pattern fits a deliberate strike list rather than a random spread. The platforms also matter, because different airframes fill different roles in a stacked plan. Beaver or UJ-26 types carry longer fuel loads, so they can reach deep and still hit with useful mass. Smaller UJ-22 units can launch in more places, so planners can fan routes and stress local defenses. Navigation can mix GPS, inertial backups, and simple visual cues, which keeps guidance alive under light jamming. Launch teams likely use dispersed pads to reduce risk, then pushed waves in short gaps to hold pressure. This pacing explains why alarms popped up in clusters rather than in a single long streak. Verification will anchor each claim because war stories must rest on more than drama. We will fix exact UTC stamps from first reports, and we will match them to satellite fire detections. We will compare thermal signatures before and after, and we will line them up with local authority notices. Refinery runs and rail flows can show the scale, while plant statements frame the repair window. Public OSINT will sit next to wire reporting, so the record stays clean when facts evolve. Those checks set the foundation for how the tactics worked under radar pressure. Layered waves overwhelm sensors because they force split attention and burn time. Low flyers hug the radar horizon and slip between ground clutter, while a second group climbs to paint a big, clean return that looks like a cruise missile on the scope. Operators must choose which track to trust, and that choice decides where interceptors go first. When priorities bend, the shield spends strength in the wrong place, which opens the door for the real threat to advance. Corner reflectors turn a small drone into a large echo, so the screen shows a target that seems fast, heavy, and urgent. A reflector sends energy straight back to the antenna, and a tiny plate can mimic a 10-square-meter shape at range. Classification software reads aspect, speed, and consistency, then flags cruise missile by design. Once that alert fires, Doctrine pushes engagement, and Doctrine consumes missiles that should guard the low lane. Saturation drains interceptors because every false return still demands a shot or a track, and both cost minutes. S-400 crews must hold illumination for semi-active guidance, while Panzer teams juggle short-range missiles and guns under pressure. Each volley takes tubes, each reload takes cycles, and each traverse takes degrees per second that cannot be cheated. Those mechanical limits create narrow windows, and those windows are exactly where the main wave aims to arrive. Low-altitude groups keep profiles flat, since flat flight cuts Doppler cues and hides in ground noise. Tree lines, riverbeds, and industrial roofs add mask, while steady throttle preserves fuel for the last sprint. If guns cue on lead angles based on regular motion, quick altitude steps break the math and push rounds behind the path. Small changes force new solutions, and new solutions eat time that the escort wave deliberately stole. Command posts also feel the load, because track files fill and handoffs multiply under multi-axis pressure. A sector radar may see 15 clean returns, yet the network must merge them with optical and acoustic cues. Mismatched IDs create ghosts, and ghosts invite redundant fires that waste scarce missiles. When control loops slow, the defense shoots late and then reloads late, which keeps the corridor open longer. Electronic warfare deepens chaos since jamming degrades GPS and voice, but it also blinds defenders to clean fixes. Drones can fall back to inertial and visual match, while batteries struggle to hold links for guidance. Short bursts of frequency hopping can sneak a coordinate through a noisy band, which is enough for a course tweak. The message is brief, the effect is large, and the timing links the vanguard with the strike group. Cost is the quiet ally, because decoys are cheap and interceptors are not, so every trade favors the attacker. A reflector costs less than a breakfast, while a 57E6 or a long-range round costs a car. Even near misses matter, since heat and shock force inspections and slow the next shot. When the magazine shrinks, Doctrine turns conservative, and conservative Doctrine yields space to the final approach. The visual story is simple. Mules carry mirrors, hounds carry warheads, and both run on staggered clocks. Arrows on a map would show tall arcs drawing fire, while flat lines skim in from a blind side. Radar cross-section balloons on command, then collapses to nothing as the real shooters cross the fence. With the decoys consumed and the tubes cooling, the last climb begins, which leads directly to impact geometry and damage control. Small, low drones are hard to spot because physics favors them, and Russian radars live under that rule. A quad-size radar cross-section near 0.1 square meter vanishes inside ground clutter, while low altitude hides under the radar horizon. X-band and Q-band sets love clean airspace, but city echoes, trees, and power lines throw false spikes. At dawn, cool air bends, returns, and raises noise floors, so thresholds must rise and tracks drop. All of this shrinks warning time, which pushes stress onto the firing cycle. Signal processing adds its own traps, and small errors snowball under pressure. Slow drones give weak Doppler, so speed filters hesitate or misclassify them as birds. Side lobe energy spawns ghosts near rooftops, and multipath in factories makes one drone look like three. If software tightens filters, it loses marginal tracks. If it loosens them, the console floods. That dilemma steals minutes from commanders, which bleeds straight into engagement geometry. Guns and launchers also live in the real world, and metal moves only so fast. A turret must traverse through degrees per second, and hydraulics dislike sudden reversals. Stabilizers fight vibration on bad roads, and bearings lag when crews overcorrect. Slew to queue sounds quick on paper, yet cross-decking from left to right costs seconds. Those seconds are precious at low altitude because targets cross short arcs and then disappear. Ammunition cycles create hard pauses, and pauses produce corridors. Short-range missiles sit in limited tubes, and reload crews need their own safety rhythm. Even autoloaders require extract, lift, ram, and confirm, which adds a minute that attackers can map. Fuses bring another limit, since many warheads arm after a safe distance, not at the muzzle. If a drone slips inside that bubble, guns must finish the job, which is exactly the attacker's bet. Fire control math struggles when targets step altitude at random, and drones exploit that gap. Predictive lead assumes steady motion, but too quick climbs change time of flight and throw aim long. Filters smooth noise with models, yet process noise grows when profiles jitter on purpose. A 3-meter vertical hop can ruin a clean solution at 800 meters, and fragments then miss the fuselage. These tiny maneuvers steal hit probability, which compounds the reload and traverse delays. Clear terms matter in this fight because wrong labels drive wrong drills. Panzer S-1 uses the 1RS-2-1E Schlem radar suite, and its strengths and blind spots match that design. Tor M2 fires the 9 M331 or newer 9 M338 family, not the Bucks 9 M38, and their guidance windows differ. Training must match the right seeker, fuse, and coverage cone, or crews chase myths instead of drones. Precision in nomenclature builds precision in tactics, which sets the stage for real fixes. Countermeasures exist, and they start with more eyes at the right height. Electro-optical and infrared cueing can watch the low lane, while acoustic arrays flag prop tone over roofs. Gap filler radars on masts, tethered aerostats, or trucks can cover dead ground without breaking the bank. True 360-degree mounts and overlapping sectors cut blind back moments, and dispersed cap holds pressure. These steps raise detection and shorten the kill chain, yet they still meet trick echoes and planned misdirection, which is where the next layer of deception begins. Electronic warfare tried to shut the raid down, yet the strike kept its course because the crews planned for a blackout. Jammers like the Krasuka 4 can swamp GPS and break command links, and they raise the noise floor so high that screens turn to snow. When that happens, a smart drone falls back to inertial navigation and camera-based matching, since gyros hold heading while vision checks landmarks. Thermal throttling is managed by cutting non-critical loads, so recognition keeps running even when chips run hot. That resilience set the stage for communication under fire. Short bursts still carry far when they hop across frequencies, and that is how a short message can survive heavy jamming. Frequency hopping spread spectrum flips channels many times per second, and a jammer cannot blanket every slot with equal power. A drone only needs a few clean milliseconds to pass a compact packet with coordinates and timing, which is enough to align a wave. Receivers use match filters to catch that whisper inside the roar, then adjust course by a few degrees. With timing restored, the formation regains shape under pressure. Guidance had to be simple and durable, because complex scripts fail in chaotic air. Inertial sensors track motion, but they drift, so visual fixes refresh them with edges of roads, rivers, and lights. At dawn, long shadows sharpen contrast, and that helps cameras lock shapes, even when smoke and haze sit low. The flight code weights every cue, then rejects outliers that do not fit the map, which keeps errors from multiplying. A clean, modest model beats an elegant, fragile one in a jammed sky. Range was the other puzzle, and engineers solved it with fuel more than with speed. Some airframes traded part of the warhead space for auxiliary tanks, and that swap cut blast size but stretched endurance. A lighter charge still breaks fragile systems when placed well, while extra fuel opens routes that bend around early warning belts. Reported runs toward Penza showed what that choice can buy, because a deep path forces defenders to guard more sky with the same tools. Greater reach turned a local raid into a theater problem. Low altitude kept the profile flat, yet a deep leg still crossed patrol zones, so evasion met interception. Combat air patrols can cue missiles with active seekers, and a clean lock should finish a slow target. But barrel rolls, brief climbs, and irregular throttle changes force seekers to chase angles near their control limits. Even a near miss sends fragments wide if timing shifts at the last second, and that buys the final mile. Survival by seconds creates the space needed for precise aim. The targets of choice were not symbolic. They were technical bottlenecks that multiply damage far beyond a small blast. A refinery unit can be bypassed, but a specialized tool line in a chip plant can take months to replace and calibrate. Filters clog, clean rooms foul, and high-value machines cannot be cleaned with hoses, so modest debris becomes a full stop. A 15-kilogram charge placed at a weak joint can remove capacity worth millions per week. Precision, not brute force, explains the industrial effect. Costs also tilted the board, because every decoy and fuel tank cost little compared with an interceptor or a fighter sortie. A few lost drones still make sense when one survives to hit a node that anchors a supply chain. Defenders then must shift batteries to guard factories, and those moves open seams at the front. Once that cycle starts, the attacker spends plans while the defender spends force, which changes tempo across the map. And tempo is the bridge to the strategic shifts that come when air defenses redeploy toward home. Air defenses are shifting inward, and that movement changes the map of the war. When batteries leave the front to shelter refineries and industrial hubs, brigades lose the shield that keeps rockets and drones at bay. Gaps appear along roads, bridges, and ammo parks, so Ukrainian fires can range farther with fewer losses. Commanders must stretch patrols to cover longer lines, and stretched lines create timing windows that smart raids can exploit. This redistribution sets the frame for how resources will be spent in the coming weeks. The math favors cheap attackers, because a low-cost drone can drain a high-value interceptor and still threaten a tank farm. Each launch forces crews to fire, reload, and inspect, while each reload slows response for the next track. A single miss still burns time and morale, yet the defender pays again when factories halt and spare parts arrive late. Budgets shift from offense to repair, and repair delays weaken pressure at the front. That financial tilt explains why deep strikes produce effects far beyond the blast radius. Energy supply feels the shock first, and regional prices react before reports are complete. If a coking unit or electrical yard sits offline, rail schedules slip, truck fleets idle, and storage draws down. Insurance risk climbs, private security costs rise, and managers harden sites with sensors and barriers that do not fight at the front. When every depot looks exposed, fear spreads faster than fire, and fear moves policy as much as numbers do. Those pressures feed directly into how forces maneuver in the field. Units without close air defense must disperse more, which lengthens resupply and slows assaults. Longer routes raise fuel burn and crew fatigue, while extra decoys and camouflage add workload to every march. A slower tempo gives Ukraine room to stack artillery cycles and rotate strike teams on a cleaner clock. Tempo, not tonnage, becomes the lever that decides who sets contact on their terms. Viewers can track the trend with open data, and these signals stand out when scans are routine. Fresh satellite heat spots over refining towns point to new damage, while sudden NOTAM or NAVWARN blocks hint at emergency work. Train manifests, pipeline flows, and export tallies reveal strain when volumes dip or reroute. Spot movements of Tor, Pantsir, S-300, or S-400 away from the front confirm the shield is moving home. Those indicators tie the local blast to the wider theater, which leads straight into the final assessment of where the fight is heading next. Speed, deception, and clean data can bend even a layered air shield, and a window of seconds can decide the whole fight. Those strikes showed that timing beats mass when planners stack waves, split attention, and land the final shot inside the reload gap. Deep targets now live under real risk, so the industrial rear becomes a front line where one hit can slow fuel, parts, and repairs. That pressure forces air defenses to move home, and every battery that turns inward leaves a seam for artillery and drones at the front. Russia will likely thicken the low tier with EO/IR watchers and gap filler radars, while electronic warfare pushes harder to blind guidance. Storage and hangars will spread out, fire breaks will grow wider, and patrol cycles will tighten around key plants. Ukraine will answer with smarter decoys and corner reflectors, better jam-resilient navigation, and wider multi-axis routes that pull shooters apart. For viewers tracking the next moves, watch fresh satellite heat spots, new NOTAM blocks, and sudden shifts of Tor, Pantsir, or S-300/400 towards cities. Those signals will confirm whether tempo is breaking the shield or the shield is hardening into a new ring. Like and subscribe to Military Force for verified maps, fast updates, and sharp breakdowns that cut through the noise.